Welcome all of you. Now we have been discussing quite a bit about product operators since last 2 or 3 classes. In the last class, we discussed a lot about rotations and rotation of a particular operator about a particular axis and what is the type of solution we are going to give. We are going to get the general solution. I said is the cosine of the old operator plus sine of the new operator with the 3 diagrams which were given to show about rotation of each of the operators about x axis, y axis and z axis. We could get a solution very quickly without going to explicit calculation of the density operator rho of t, which is equal to e to the power minus h of t, rho of 0 into e to the power of I h of t. We do not have to go through all this rigorous thing and use trigonometrical identities, everything, but it is clearly available. We worked out for the one pulse sequence wherein we apply a 90° x pulse and start collecting the signal, and we saw that by product operator analysis applying a 190 pulse for the z magnetization, which is in thermal equilibrium, the magnetization was brought to minus Iy axis, and then with the time t, when we saw the free position during the time delay during acquisition time, we found it generates x and y components, cosine and sine components, and that means the spin vector starts fanning out in the xy plane. And exactly when alpha is equal to 90°, it comes to minus y axis. At t is equal to 0, immediately after the pulse, magnetization is along minus y Iy, that is minus y axis, and then with time it creates mx and my components, that is cosine and sine components. And then we wanted to extend this further for spin echo analysis. Spin echo is nothing but 180 pulse tau, 90 pulse tau, 180 pulse tau. So 90 pulse to tau, what happens after 90 pulse and free position we already understood. Next, the effect is we have to see what happens if you apply 180 pulse, how we are going to refocus offsets, because we are not worried about couplings here, we are taking uncoupled spins, in which case we do not have to worry about coupling. If at all there is a refocusing, it has to be offset or chemical shifts. So now we will continue further from that with 180 pulse. Now we wanted to find out in the second step effect of 180 pulse and free position after 180 pulse. Okay. So this is the solution we have got up to t, time t, after the 90 plus first tau during free position. The pulse along x does not affect x, so we do not have to worry about Ix. Hence we have to consider only Iy term. I told you Ix pulse about x, the Iz pulse about z, all those Iz on z will not have no effect at all. Z pulse along z, x pulse along x, y pulse along y has no effect. Okay. So now we will consider only minus cosine omega of t and how it evolves with the 180 pulse. Of course, we have to see the figure, go back to the drawing. You have to see what is now it is the rotation of Iy about Ix. So Iy term is there. We are rotating about x axis because we are applying a 180 pulse along x axis. So this is the term we are going to get if you see the figure. Minus cosine omega t is there and Iy is rotated, and we are going to get cosine omega tau pi into Iy plus sine omega tau pi into Iz. And this is the Hamiltonian for pi rotation, 180 pulse about x axis. Same omega 1 Tp is equal to omega 1 Tp, but now t is 180°. So it is why it is written as t pi. So use this diagram. Pi, omega 1 t pi is equal to pi pulse width, cosine of pi is equal to minus 1, sine of pi is equal to 0, substitute it there. Then in the arrow rotation we can say the application of pi pulse along y axis gives you minus cosine omega of t, this is minus 1 and this is sine pi 0, this term will go and we are going to get only minus 1 into Iy. Minus 1 into Iy, this will finally minus into minus, it will turn out to be cosine of omega t into Iy. This is what we are going to get. Okay. This is the application of 180 pulse after the first tau delay. Okay. What does it do? The pi pulse has simply inverted the Iy. From minus Iy it became plus Iy, that is all. Okay. Now the effect of pi pulse, if we have seen, this term was remained unaffected, we have to now consider that. Okay. Next step is to calculate the free position after the 180 pulse. This is what we got with the 180 pulse. Now this term unaffected we considered because you can't ignore that. Now the total precision during free precision during second term you have to consider. During free precision above both the term you have to consider. First term will take cosine of omega t into Iy. Okay. Again that means rotation of Iz is rotating about Iy. So now I am sorry, Iy is rotating about z axis. Rotation of Iy about z axis you write cosine omega t into Iy minus sin omega t into Ix by using this formula. Cosine of the original operator Iy and sin omega t of Ix. Ix when it is rotated about z axis which goes to rotation of Iy rotated goes to minus x. So it will become minus of sin Ix. Okay. So this is what we are going to get. Iy when it is rotated during free position about omega t into Iz about the z axis, omega t is the offset with the time and t is the time, you are going to get omega cos omega of t into Iy minus sin omega t into Ix. This is the first term. All we did is rotated Iy about z axis. So this is what cosine omega t into Iy. Now I will take cosine omega t, there is a multiplication is still there. We cannot ignore that. Now we only saw rotation of Iy. Now it turns out to be this is the solution of rotation of Iy with cosine of omega t. You are going to get cosine omega t into Iy minus sin omega t into Ix. This is what the solution you are going to get. Okay. So this is what for the first term. Now let us see second term. Second term is sin omega t into Ix. What is happening here? You are rotating Ix about z axis. Now the rotation is about z axis during free position. Ix is rotated about z axis. This is drawing you have to use. This is the figure. Now you are rotating Ix about z, it will go to Iy. That is the solution. So Ix when is rotated about Iz with omega into t is the offset. See now cosine of omega of t into old operator plus sin omega t into new operator is Iy. This is the solution for it. So now sin omega t into Ix if you take that product was also there, sin omega t which you cannot ignore. Now during free position this turns out to be sin omega t into cosine of Ix, cosine of omega t into Ix plus sin of omega t into Iy. This is what you are going to get. Now we have to bring both the terms together. We have evaluated individually each of these terms. Now combine both of them. We have to see what is the effect of that. Now bring both the terms together. This is the term which you obtain in the first one. This is the term you obtain in the second one, sin omega t into cos omega t plus sin omega t into sin omega t into Iy. This is what the term you are going to get. But interestingly you can see this term will cancel out, plus and minus. So what you are going to left with is cosine omega t into cosine omega t into Iy, sin omega t into sin omega t into Iy. Okay. So what is this? Cosine omega t into cosine omega t is cosine square omega t. This is sin square omega t. Now take out Iy as a common factor. What are you going to get? Cosine omega square plus sin omega square. What is cos square theta plus sin square theta? Is 1. So this term turns out to be 1 and solution is going to be 1 into y, that is y. So what happened now? See what happened is when you did this 180 pulse, when you applied 180 pulse and allowed to evolve for equal amount of time, another time period t, and then you work out during free position, what happened? The magnetization remained is Iy. What happened? The spin echo refocuses the offset and the magnetization appears along y axis. The chemical shift term will go, it is not there, offset term is not there, it is removed. Only the magnetization which is minus along minus y axis is brought to y axis. This is called refocusing of the offset or chemical shift. This is the, please remember this. Now we are considering the homonuclear case. Now in the spin echo sequence, that is 90 tau 180 tau sequence, it refocuses the offsets or chemical shifts and make sure that the magnetization which is along minus y goes to plus y axis. That is the spin echo sequence. Diagrammatically you can understand like this. Look at it, what is happening? The magnetization which is along z axis is brought to minus y axis by applying an RF pulse along x axis. That is what we did. And then at the end of the second delay, this is what happens. the magnetization has come back to plus y axis. This is what is called an echo. How it works out, you can see vectorially like this. There is a vectorial picture. We will see at different we have worked out by product operators. By different sequences, vectorially also we can understand to get a picture. But we can't do this for all pulse sequences, complicated sequence easily. It is a very complex thing. But just for this I will show you. We start with different time periods A, B, C, D, etc. I call them A, B, C, D. I call this as E. At A, what is the state of magnetization? At A, it is in thermal equilibrium along z axis. A is in this is a situation, magnetization is along z axis in thermal equilibrium. At B, what is happening? You are applying a 90-degree pulse, you brought the magnetization to minus y axis. That is the state of magnetization at B. At C, what is happening during the time period? There is a dephasing. We said magnetization start fanning out. It creates cosine and sine components. Oscillatory components will be produced as a function of time as time evolves. So now magnetization vector start moving on either time. First this one which moves this side, other which moves other side. We call them as fast moving and slow moving components. They higher one are the higher frequency, other is at lower frequency. They start moving in the opposite direction. This we call it as fast moving and slow moving components. Now after certain time, now we are going to apply 180 pulse. With the 180 pulse, what you are going to do is simply invert the magnetization from plus y to minus y. The entire the vectors which are here, it is like turning a pancake. You completely turn it on other side from minus y axis to plus y axis. Then what is happening is the fast moving and slow moving components interchange their direction of motion. They start moving in the opposite direction now. Fast moving earlier it was going like this, slow was moving like this. Now fast starts moving like this, slow starts moving in the opposite direction. Then what is going to happen? After exactly same amount of time, they will come back, refocus along y axis. So the vectors get refocused under plus y. Started with minus y, for a given time they start defacing and created a cosine and sine components and apply 180 pulse, invert the magnetization from minus y axis to plus y axis. Fast and slow moving components start moving in the opposite direction, and after exactly same amount of delay they refocus along y axis. This way, this is the diagrammatically how it works, can be seen like this. Animation of a spin echo, it is like this, you see like this. Now magnetization is along z axis, 90 pulse brought like this, and then you rotate by 180 pulse and they can go back and assemble. Fantastic. This is what is called spin echo sequence. Okay. Now we got some hang of how to analyze the pulse sequence using product operators. But remember, till now we have taken a single spin or any more spins without any J coupling. There is no interaction between the spins. You are only concentrating on evolution of the magnetization under free precision or under offset. Now consider a case of a coupled spin system. Take example of two coupled spin system. Again weakly coupled A and X spin, or we call it 1 and 2, doesn't matter. This is a weakly coupled case. Now for a single spin, there are 4 operators. Of course, we know I1x, I1y and I1z. There is also called unity operator E1. Of course, practically it does nothing. It only helps in mathematical operation. Okay. For a second spin, there are 4 operators. Again, I2x, I2y and I2z, and a unit operator E2. Okay. So for a second spin, there are 4 operators like this. Now when 2 spins are interacting, we consider all possible combinations. We have 4 operators for spin 1, 4 for spin 2, 4 into 4, we have 16 operators are there. The 16 operators are needed to describe the state of 2 spins completely. So we have to take all the possible products of this when we work with coupled spins. All 16 operators we have to consider. That is the reason, since we get product of all these things, these are called product operators. Why product operator name comes? Because when you consider multiple spins, or example of 2 spins here, each spin has 4 operators. We have to take combination of all the 4 with all the remaining 4 other operator, other spin. So, we will have 16 operators, that is why they are called product operators. Now, what are the operators we require for two coupled spins? One thing is Ix, Iy and Iz are the xy and z component of the nuclear spin angular momentum, that we know, Ix, Iy and Iz. And with E1, considering E1 also, E1 is a unity operator. As I told you, its reason is only to simplify the mathematical operation, unity operator is there. With E1, now what are the four possible product operators? E1 into E2 for the second spin, E1 into E2, E1 into E2x, E2y and E2z. Because now I am considering for the second spin, E2, I2x, I2y, I2z are the three operators, angular momentum operators. When it combines with E1, we get four possibilities: E1 into E2, E1 into I2x, E1 into I2y, E1 into I2z. With Ix, I1x of the first spin, first x component of the angular momentum of the first spin, again four combination, I1x, E2, etc. like this. I1x, 2 times I1x, I2x. Now the question here 2 comes. It is only for normalization, don't worry, that is a number. Okay. Similarly, with I1y, we have 4 operators. I1z, we have 4 operators. So, 4, 4, 4, 4, there are 16 operators we have generated together, we only have 2 spins. Okay. The unity operator, as I said, nothing, it only helps in mathematical operation. What is the 2 I told you? It is for normalization. When there is product of 2 operators, 2 comes, we use it for normalization. Okay. So, now if I have to consider the density operator at any time when the 2 spins are interacting, including J coupling, it is a linear combination of any of these. All the 16 operators are there, it is a linear combination of any of these together. What do these operators stand for? How do you understand these operators? See, I1z is a Z magnetization of spin 1, I2z is called Z magnetization of spin 2, I1x is called in phase X magnetization. Please remember, I1x is in phase, that is a word I am stressing, it is an in phase X magnetization of spin 1. Similarly, I1y is the in phase Y magnetization of spin 1. I2x in phase X magnetization of spin 2 and I2y is in phase Y magnetization of spin 2. 2 I1x, I2z, this product if you consider, it is an antiphase X magnetization of spin 1. You look at the spin 1. Okay. For spin 2, it is along Z axis here. Spin 1 is along X axis. This is called antiphase X magnetization. If the same thing is along Y axis, it is called antiphase Y magnetization of spin 1. You understand? Similarly, if I consider I2x and I1z, for the second spin also, we have antiphase X magnetization of spin 2 and antiphase Y magnetization of spin 2. This is what each of these operators mean. Now, there are also combination of other operators like this: Ix into 2x, Ix into 2, I1x into I2y, I1y into I2y, I1y into I2x. Here, both the x and y operators of both the spins are present in the xy plane. These products are called multiple quantum terms. Since there are 2 spin operators, we are considering it is a double quantum terms. And the product 2 I1z and I2z is called a non-equilibrium magnetization along Z axis. It is a non-equilibrium magnetization. That is all. You do not have to worry about it. Okay, that will not generate any observable magnetization. Okay, this is what it is. And when we have a single spin for final density operator, we have to consider the effect of pulses and free position. But when we have 2 spins, the new feature is we need to consider J coupling also, that has to be included. Okay. So, now vector representation of all these 2 spin operators can be made. This is what we said, I1z, I2z, what are the I1x, I2x, etc. Graphically also we can see how are they. Okay. So, we can represent vectorially these 2 spin operators. For example, if I write like this is I1z, the the two J split multiplets are along z axis. This is a I1Z, the z magnetization of spin 1. This is called z magnetization of spin 2, both along z axis. Here in phase x magnetization, both along of spin 1, let us say, both along x. This is in phase x magnetization of spin 2. I have given you different color, of course this should have been red. I have for all the spin 2, of course it does not matter, it is only color code is only to make us understand clearly. This is for spin 2. Now this is I2y, this is I1y and this is I2y. The in phase y magnetization of spin 1, this is in phase y magnetization of spin 2, and this is important, x magnetization and y magnetization, z magnetization here, 2 I1x and I2z. This is for spin 2, this is for spin 1. This is antiphase x magnetization of spin 1. Remember, spin 1 has x magnetization in the antiphase, and this is z magnetization of y spin, or I am sorry, z magnetization of spin 2. Similarly, for spin 2, x magnetization is antiphase like this, and for spin 1, z magnetization is antiphase along z axis. Remember, one thing you should clearly understand, these antiphase terms are very very important, especially for transferring the spin polarization in experiment involving polarization transfer. Please understand, 2 I1x and 2 I2z, 2 I1x into I2z means it is antiphase x magnetization. See, x or components are antiphase along x axis, and for spin 2 it is along z axis. Spin 1 along z axis, spin 2 along z axis, both are antiphase. For this spin 2, x component is spin 2 which are antiphase, and for spin 1 z component is antiphase like this. Similarly, antiphase y magnetization of spin 1 and 2. Now spin 1, both the vectors along antiphase along y, z is antiphase along, for spin 2 antiphase along z. Similarly, I2y and I1z, it is for second spin, y magnetization is antiphase, for spin 1 z magnetization is antiphase. And here 2 I1x and 2 I2x, both x and y, I am sorry, both x components of both spin 1 and spin 2 are antiphase. Please understand, x components of both spin 1 and spin 2 are antiphase, that is 2 I1x I2x. Similarly, 2 I1y and I2y, for spin 1 and spin 2, both the y components are antiphase like this. These are called multiple quantum terms, or in our case it is a DQ term, double quantum term, because both these spins are either along y axis or x axis antiphase with each other. So now continuing further, I can write 2 I1x and I2y. That means spin 1, both x vectors are opposite, antiphase, whereas spin 2, they are in y axis, antiphase. Similarly, to I1y and I2x, spin 1 is antiphase along y axis, spin 2 is antiphase along x axis. All these are called MQ terms. E1 and E2 is nothing but just a vector representation for mathematical operation. This is diagrammatically represented like this. So the free precision Hamiltonian for two coupled spins we have to consider now. Okay. Terms to be evaluated are free precision of two spins. Now when I consider first free precision of spin 1, that is the Zeeman interaction along rotation about z axis, omega 1 iz, and then omega, this should be omega 2 iz, that is our spin 2, and then j coupling 2 pi j1z and j2z. These are the terms which you need to evaluate. So initial density operator now evolves with time. Initial density operator rho 0, when it evolves with time, finally what we have to evaluate is rho of t. Okay. Now rho of 0, first evolution of spin 1 under offset, omega 1 into t I1z, omega 1 is the offset at with time t, how it is evolving we know, and this is for the spin 1, that is first one. Okay, evolution of spin 1 under offset. Now evolution of spin 2 under offset is again omega 1 into, it should have been omega 2 again, I am sorry, it is a mistake, omega 2 into I okay, it's frequency of the, if I have taken it one same, does not matter, it should be omega 2 t into I2z. This is evolution of spin 2 under offset. The offset could be same, need not be same for both omega 1 and omega 2, they could be different. And also third term is evolution of J coupling, J1z into J2z. So, this is the evolution of the coupling term, this is the evolution of offset under spin 2, evolution of offset under spin 1. As I said, evolution of each of these terms can be considered individually and sequentially under pulses and free precision both. Applying pulse individually you can take evolution of spin 1 and spin 2, there is no correlation between the, when you are considering spin 1, spin 2 can be ignored, when you are considering spin 2, spin 1 you do not have to worry. Similarly, when you are evaluating evolution of chemical shift, you do not have to worry about J coupling, when you are evaluating J coupling evolution you do not have to worry about chemical shifts. So, all these rotations have to apply to each spin individually and they are in the order in which it is evaluated is immaterial, that is very important. And when you are considering the rotation of spin 1, it does not affect the rotation of spin 2. Similarly, when you are considering rotation of spin 2, rotation of spin, it does not affect spin 1 at all. Rotation of spin 2 does not affect spin 1. So, both are important points. In order in which you evaluate whether chemical shift first or J coupling first, free precision, all those things does not matter. Okay. Individually of spin 1, spin 2 and chemical shift J coupling, anything you can do in any order. And another important thing, rotation of spin 1 does not affect the rotation of spin 2 and vice versa. Now, let us consider the evolution of I1x. What is I1x? Under offset of spin 1 and offset of spin 2 and J12. What is I1x? It is in phase X magnetization of spin 1. I told you it is in phase X magnetization, diagrammatically I showed you. I1x is for first spin 1 in phase X magnetization. Now, let us see how does it evolve under offset. So, now what is that evolving? Rotation is about Z axis. Okay, evolution of I1x, rotation about Z axis. So, I1x when it rotates about Z axis it goes to Y. So, cosine of the old operator it becomes cosine omega 1 t I1x plus sin omega 1 t I1y. This is I1x I am considering. Now, allow this term to evolve under the offset of spin 2. Now, these two both have to be evaluated under offset of spin 2. Now, what is going to happen? Absolutely no change you will see. The reason is, as I told you, this when you are rotating spin 1, when you are considering rotation of spin 1, it has no effect on spin 2 and vice versa. So, now you are rotating considering rotation of spin 1 and its effect on spin 2 is not there at all, it is ignored. So, that is why no change is there, you can ignore, it does not affect spin 1. Now, overall evolution under both the offsets is given as omega 1 t I1z and omega 2 t I2z should be equal to this t I2z. Now, it should be like this sin omega 1 t I1x plus sin omega 1 t I1y because this has no effect. Step 3, evolution of I1x and J coupling. Under J coupling we have to see there are now two new identities introduced. In phase term we have considered evolution of I1x under omega 1 t I1z, omega 2 t I2z that we have considered. Now, evolution of the same term under J coupling. So, that means these two terms we should be considered under J coupling evolution. Okay. So, in this case the two new identities are introduced like it was introduced for the single spin case. Remember, 3 drawings were given finally to summarize this thing. Exactly these two terms are new identities are introduced. This is cosine of I minus I theta into I1z I2z into Ix is into this one is given as cosine of theta by 2 into I1x plus sin theta by 2 into I1y I2z. Similarly, rotation about y axis This is what it is. So, this is for the rotation of about I axis, rotation of Ix, and this is rotation of Iy. These are the things we have to consider. Now, Ix, what do you understand from this? When Ix is evolving under J coupling, remember it evolves into this one. Ix, when it evolves, the in-phase term evolves into I1y, I2z. What is I1y, I2z? I told you it is an antiphase term. Ix evolves into I1y, I2z. Similarly, Iy evolves into I1x, I2z. Both are antiphase terms and both are in-phase terms. What it means under J coupling, in-phase terms evolves into antiphase terms. The in-phase magnetization became antiphase magnetization because of J coupling evolution. Okay. So, under J12 Hamiltonian, if you write how the evolution of Ix takes place, this is the formula. Ix is being rotated under J12, in which case this is the identity we have to use. Now, Ix component, which is in phase, turned out to be antiphase. Now, exactly at theta is equal to 2 pi j period for which spin vector, tau is the period for which spin vector evolves. We can work it out what happens if theta is put this value in this theta and calculate cosine and sine terms. Okay, now, we will start with Ix and allow it to evolve under coupling for tau. I started with Ix and see Ix means it is the first one you have to consider. First identity you have to consider because that is the rotation about I axis, rotation of Ix. Okay. So, now we have first term we have to consider. I am worried about Ix which is rotated under J coupling. Okay. So, now with that if I consider, go to the next one here, consider Ix, allow it to evolve under coupling for a period tau. We are using the first identity, this is the first identity, and now theta is equal to pi j into tau. J12 is the between 1 and 2 and that is j, theta by 2 is equal to pi j into tau. So, now I am evolving I1x, in phase magnetization of spin 1, in phase x magnetization of spin 1 under J coupling, you get cosine of I1x of this term into I1x, sine of this J term into antiphase term. This is what you are going to generate. Now, put tau is equal to 1 over 2 j here. What happens 1 over 2 j? This gets cancelled out j. It will become pi by 2. What is cosine of pi by 2? 0. So, we are going to left with only again here tau is equal to 1 by 2j if you put this j will cancel out, pi by 2 you get, sin pi by 2 is equal to 1. So, you are going to left with only this term. Exactly when tau, the delay for which you allow this coupling to evolve is 1 over 2j, then in phase term became antiphase term. Very important point. The in phase term became completely antiphase at exactly tau is equal to 1 over 2j. And this is diagrammatically you can represent the coupling evolution like this. For example, I1z, I2z, if it is evolving like this, I1y and I2z if you consider, now y and z if you consider, y is the first spin, z is the second spin. Now, I am considering y and z which is rotating like this in this direction now, when it evolves under J coupling. So, this is going to be minus Ix, you put it minus I1x, and now this is the antiphase term. So, exponential of this term if you put it, if you work it out using diagram, it turns out to be, now what I am doing, this 2 I1z I2x is evolving under I2z and I1z and I2z. The solution is cosine of theta by 2 into 2 of I1z I2x plus sin theta by 2 into I2y. Very simple. So, what we worked out for the spin 1, this is for spin 1 we worked out. We took the spin 1 evolution under offset and then under J coupling. Now, if you, what about spin 2? I said both can be individually taken. Individually you can calculate. Rotation of spin 1 doesn't affect spin 2 and vice versa I said. Now what happens if I calculate spin 2? Identical term you get. Only thing is indices which you saw here get interchanged. 1 become 2, 2 become 1, that is all. Here 2 become 1, that is what is going to happen. Okay. So, indices get interchanged when you work it out for spin 2. So, now we can work out how does in-phase term evolves after this. So, now since the time is getting over, what I am going to do is I will stop here. We will come back and continue the evolution of in-phase term and then work out how product apparatus can be applied for heteronuclear case and in the case of two spins the J coupling is present. So, right now we have understood quite a bit about product operator, especially when J coupling is taken into account. We got product operators diagrammatically we represented. We understood I1x, I2y and I2x, I1y, I2y, all those things are called in-phase magnetization of x and y for spin 1 and 2. Similarly, we understood what is the antiphase magnetization I1x, I2z, I1y, I2z, I2x, I1y, I1z, I2y, I1z, all those things they are antiphase terms. Similarly, I1x, I2x, I1y, I2y, I2x, I1y, all those terms are called multiple quantum terms. So, all those there are 16 possible combinations we could see. There are product operators when there are two spins coupled with the two spins evolution we have to consider under J coupling also. So, now under J coupling all the 16 operators will be there and how it evolves can be given. We understood to taking a simple example of two spins which are coupled, how they evolve under the offset and J coupling. And then we understood in this when you consider the evolution of the J coupling, the in-phase term turned out to be anti-phase term, very interesting. When we took I1x term, evolution of I1x term, the in-phase term of spin 1, and during J coupling we found it turned out to be antiphase term. So, same thing happens to I2 y term also if you consider or for spin 2 also. So, identical things we are going to see. So, now we are going to understand evolution of in-phase terms. So far we understood how in-phase terms evolved everything, how it became anti-phase terms. We will continue further understand few more concepts that are involved in this. So, I will stop here, we will come back and continue in the next class. Thank you.